Welcome. This video kicks off a new playlist on series solutions for second order linear differential equations. In this video, you will learn how to differentiate higher order derivatives using Leibniz theorem. So let's introduce a short annotation where y subscript 1 will be representing dy ds, which is the first derivative of y. Y subscript 2 is equal to what? D square y over ds squared, that is the second derivative of y. And y subscript 3 is equal to d cube y over ds cube. Note that if the order of derivatives is greater than a degree of s, then the derivative is 0. So for example, if our y is equal to s squared, that is s power 2, our first derivative is equal to what? 2s, applying the basic differentiation formula. Then our second derivative is equal to what? 2. Now 2 is a constant. If we find the derivative of 2, we'll get a 0, because the degree of s squared is just 2. When we find the third derivative, fourth derivative of or higher derivative, our result will be what? 0. So Leibniz theorem provides a formula for finding the nth derivative of the product of two functions. For example, if y is equal to uv, where u and v are both functions of s, so our first derivative will be equal to what? uv prime plus vu prime, which is basically the product rule. But how do we arrive at this solution? Let's say we start by picking a term. Let's say we pick u, then we multiply by the derivative of the other term. So the derivative of v will be what? V prime. Plus, we'll do the same thing. Now we reverse the terms. So because we picked u before, now we'll be picking v. When I write down v, I'll multiply by the derivative of the other term, which is u. So which is the derivative of v is what? U prime. That's how I arrive at u v prime plus v u prime. So if I want to find the second derivative of this function, of this solution now, we'll do the same thing again. So to find the derivative of u v prime, let's say I write down u, then I multiply by the derivative of v prime, which is what? V prime prime. So I add u v prime prime plus, now I write down v prime and multiply by the derivative of u, which is what? U prime. So because I want to arrange them alphabetically, I wrote u prime v prime, u before v. Now plus, moving on to vu prime, the derivative of vu prime is what? Well, let's say we write down v first. We'll multiply by the derivative of u prime, that is what? U prime prime. Plus, now you write down u prime and multiply by the derivative of v, which is now what? V prime. So after that, we collect like terms. We can see that, okay, u prime v prime occurs twice, so I wrote them together and added the coefficient, which gave us y prime prime is now equal to what? U v prime prime plus 2u prime v prime plus u prime prime v, and that is the second derivative of y. And you also notice that this is related to the binomial expansion using Pascal's triangle, because for second degree we have the coefficient as 1, 2, 1. You get that? Leibniz theorem states that if y is equal to uv, the expression for the nth differential coefficient can be written as y subscript n is equal to unv plus n u n minus 1 multiplied by v1 plus n multiplied by n minus 1 over 2 factorial multiplied by u n minus 2 multiplied by v2 plus n open bracket n minus 1 multiplied by n minus 2 divided by 3 factorial multiplied by u n minus 3 multiplied by v3 plus, okay, we keep adding up the series until we get to a finite solution. So this solution can be minimized into u subscript n multiplied by v. Don't forget that these subscripts are representation for what? The degree of differentiation, plus n combination 1 multiplied by u subscript n minus 1 multiplied by v subscript 1. Now I can see that n combination 1 is representing this coefficient n, and right here the coefficient n open bracket n minus 1 over 2 factorial is being represented as what? N combination 2. So how do we arrive at that? Using the formula of this combination formula, which says that n combination r is equal to n factorial over n minus r factorial multiplied by r factorial. So if I want to find the value for n combination 1, I get this. So that is what n factorial over n minus 1 factorial multiplied by 1 factorial. And now n factorial translates into multiplying n by its descending terms, which means it can extend into n times n minus 1 times n minus 2 times n minus 3 into infinity. But since we have n minus 1 as a denominator, as a factor in the denominator here, I can easily stop at n minus 1 factorial at the numerator. So both of them cancels out, and now n combination 1 is equal to what? N. Same thing for n combination 2. So in other words, if y is equal to uv, our y subscript n can now be equal to the summation from r is equal to 0 to n of n combination r of u subscript n minus r multiplied by v subscript r, where u and v are functions of s. So you will notice that this thing is this formula is still related to binomial expansion of what Pascal triangle, whereby the differential coefficient of u is decreasing by 1. See, I have un here. Now it is what? Un minus 1, un minus 2, while the differential degree of v is what? Increasing by 1. That's just it. Now we need to know the choice, the condition for choosing our u and v. So now v is the one whose derivative eventually becomes 0 after a number of successive differentiation. Just like the example I gave before, that y is equal to s squared. So for this function now, I know that after performing a derivative of the third order, then I will have what? 0 as my answer. So that means in a question like this, if I have an algebraic function, then that will be my what? That will be my v. Then the other one should be my u. Now u is the one whose nth differential coefficient can be easily obtained. Example 2. Find the n derivative of y when y is equal to s raised by 3 multiplied by exponential 2s. So first thing is to identify the u and v functions. So obviously our v is equal to what? S raised by 3, because upon getting to the fourth derivative of s raised by 3, the output will be equal to 0, and that gives us an idea that the series solution will end at the third derivative. So you get where the yn is coming from. So we'll be having a finite solution at what? Y subscript 3. Now our u is equal to exponential 2s. So the nth derivative of u will be given as 2 raised power n exponential 2s. How do I know that? Now normally if I'm supposed to find the first derivative of u, that is u subscript 1, it will be equal to what? 2 exponential 2s. That is using chain rule. And our u2 will be equal to what? 2 times 2 is now 4 exponential 2s. And our u3 will be equal to 8 exponential 2s. So you notice that the coefficient is increasing by a factor of 2. So which is why the u subscript n is given as 2 raised power n exponential 2s. Now we have to write out the derivative of v and u. For our v1, our first derivative of s cubed is equal to what? 3s squared. The second derivative is equal to what? 6s. How do I get that? That is 2 times 3, then s. And the third derivative is just 6, a constant. So you notice in the derivative for v, the derivative is increasing, while for u, the derivative will be decreasing. So now we start with u subscript n, or un. So now our u subscript n is equal to what? 2 raised power n multiplied by exponential 2s. Now what we'll be getting now, we will not be finding u subscript n plus 1. We'll be finding u subscript n minus 1. It is decreasing by 1. So which is just substitute anywhere there is n, substitute n minus 1. So now we have 2 raised power n minus 1 multiplied by exponential 2s. And now for u subscript n minus 2, you just substitute n minus 2 in the as the power of 2, and same thing for 3. And now we apply it into the Leibniz theorem, which says that the n derivative of y is equal to u subscript n multiplied by v plus n times u subscript n minus 1 multiplied by v subscript 1 plus n multiplied by n minus 1 over 2 factorial multiplied by u subscript n minus 2 multiplied by v subscript 2 plus n open bracket n minus 1 close bracket open bracket n minus 2 over 3 factorial multiplied by u subscript n minus 3 multiplied by v subscript 3. So we'll be stopping at v subscript 3 because that is the highest degree of differentiation we can do, yeah, for this particular question. So now substituting the values, I have y subscript n equal to, so my u subscript n is now equal to what? 2 raised power n multiplied by exponential 2s multiplied by, now my v, what's our v? Our v is s raised power 3, so that is multiplied by s raised power 3 plus, I have n here as a coefficient, so just return that n multiplied by u subscript n minus 1, it is here, this is it, so that is 2 raised power n minus 1 multiplied by exponential 2s times v subscript 1. V subscript 1 is equal to what? 3s squared. Now plus this coefficient here, n multiplied by n minus 1 over 2 factorial. Now 2 factorial is equal to what? 2 multiplied by u subscript n minus 2, this is it, yeah, 2 raised power n minus 2 subscript multiplied by exponential 2s, so I wrote it here, then multiplied by v subscript 2. Where's the value for v subscript 2? It is what? 6s, so I have it here also, plus, now in the formula I have just for the third derivative, so the coefficient here is what? N multiplied by n minus 1 multiplied by n minus 2, I have it here also, over 3 factorial is equal to what? 3 times 2 times 1, which is 6, multiplied by u subscript n minus 3, which is this value here, that is 2 raised power n minus 3 multiplied by exponential 2s times, or multiplied by, where is the formula again? V subscript 3, and now v subscript 3 is equal to what? 6, so multiplied by 6. Moving on, we just have to simplify and factorize. So using the index rule, I wrote that a raised power n can be written as a raised power n minus k multiplied by a raised power k, because when we add the index, negative k and positive k cancels out and we still have what? A raised power n. And from the previous slide, we have two recurring factors, exponential 2s and multiples of 2. So we have exponential 2s here, we have exponential 2s here, we have exponential 2s here. We also have the multiples of 2. We have 2 raised power n, 2 raised power n minus 1, 2 raised power n minus 2, 2 raised power n minus 3. So let's say n is equal to 3. So 2 raised power n will be equal to 8, 2 raised power n minus 1 will be equal to 4, 2 raised power n minus 2 will be equal to what? 2, and 2 raised power n minus 3 will be equal to 1. So I can say that 1 is a factor of 1, 2, 4, 8. So we'll factor out 2 raised power n minus 3 and exponential 2s. So, but if I factor out 2 raised power n minus 3 from 2 raised power n, what will be the remainder factor? So that is why I wrote it like this, that 2 raised power n can also be written as 2 raised power n minus 3 multiplied by 2 raised power 3, and which can be written as 8 times 2 raised power n minus 3. So now when I factor out 2 raised power n minus 3 from 2 raised power n, what I have left to be what? 8. Now when I factor out 2 raised power n minus 3 from 2 raised power n minus 1, what we have left is 2 raised power n minus 1 can be rewritten as 4 times 2 raised power n minus 3. Same goes for 2 raised power n minus 2. It can be rewritten as this, 2 raised power n minus 3 multiplied by 2 raised power 1. So the remainder factor will be equal to 2. That means 2 raised power n minus 2 can be split into 2 and 2 raised power n minus 3. You get? So now let's factorize exponential 2s and 2 raised power n minus 3 from the solution. So from the first term here, when I factorize exponential 2s and 2 raised power n minus 3, this one cancels out. This 2 raised power n will be left with what? 8. So we have just 8s cubed here. For the second term, this one, the exponential 2s cancels out. 2 raised power n minus 1 gives us 4. So I have 4 times n, that is 4n, times 3, that is 12s squared. Let me see. Okay, 4n times 3s square. And for the third term, I have 2 in the denominator here. These 2 can cancel out 6, abi we'll be left with 3. Especially 2s cancel out. Now for 2 raised power n minus 2, the remainder factor will be equal to 2. So I have 2 times 3 times n minus 1. Let me check. Okay, 2 times 3 is 6s, then the n times n minus 1 also. And for the last factor, last term rather, this 6 here can cancel out. The 6 at the denominator and the 6 at this numerator, they cancels out. Then especially 2s also cancels out, and 2 raised by n minus 3 also cancels out. So I'm left with what? N open bracket n minus 1 open bracket n minus 2, and that's what I wrote here. So I just brought them together, and our final answer is equal to what? Y, the n derivative of y is equal to exponential 2s multiplied by 2 raised by n minus 3 open bracket 8s cubed plus 12ns raised by 2 plus 6ns open bracket n minus 1 plus n open bracket n minus 1 close bracket open bracket n minus 2. So this brings us to the end of this video. So stay tuned for the next video, where we will tackle some examples and really master this concept. Don't forget to like and subscribe so you don't miss it.